Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics.
Welcome to Speaking of Reliability. This is Dianna.
And this is Fred Shankleberg. And Dianna, you were just talking about a test plan sequences or some, what was that about? I only caught a little bit and I said, oh, we should hit record.
Yes, we, sometimes we create some pretty complicated test plans in order to save time or to save parts. And maybe not necessarily reliability engineers, but just engineers in general.
Mm-hmm.
And there's been some instances in my past work career where, the test plan sequence looked okay on paper. But then when we got into executing it, there were lots of hiccups that were, I guess you could say, in hindsight, you could expect them. But we really didn't plan for it ahead of time. And in one case, there was a liquid being used to perform a test. And then those parts were supposed to immediately be cut apart and then tested in another way.
Mm-hmm.
And those tests were supposed to be independent. But then what happened is that the parts got put on a shelf somewhere because another project came in and took over all the test lab. And these parts just sat in this liquid until it was test time again. And then we were getting all sorts of wonky failures. And it just wreaked havoc on everything. We had to do a special root cause analysis and verify our root causes, and just finding out what the problem was that these parts were essentially, there's a little bit of degradation or there's an effect to the parts because they were sitting on the shelf. So I just remember this as a very frustrating experience for the whole team. And lots of lessons learned. So I wanted to ask you if you've experienced stuff like this, where you just have these complicated test plans that are bumping into each other and just wreaking havoc.
Well, there's all kinds of ways that you set up, like I've heard it called a waterfall, where you have 10 components and then you precondition it under these 3 different scenarios. And then, 3 samples go this way, 4 samples go that way for different tests. And then you do the most destructive testing last.
Yes.
And you hope you run the gauntlet. And part of the logic is that in the field, you have temperature and humidity and vibration all simultaneously. But in the lab, that's expensive and or difficult to do in a meaningful way. So in an accelerated way, so we do them separately. We happen to have a thermal chamber and we have a humidity chamber, but doesn't control temperature. And then we have a vibration table. So we run them all separate. And it's a quick analogy of why we would do something like that. I've had it where the first test was not expected to be all that harmful to the product, completely destroy it. And so we had 9 more tests lined up for all these samples, but we didn't have any samples left. And, it was like, and then of course we got the question of, well, you overstressed it. Of course they all failed and they didn't change the design, and it failed miserably in the field. But there was one that was on the storage thing and it was, and I know I've talked about this group before a couple of times, but they made it was a wrist worn device, sort of like a fitness tracker of some sort.
Okay.
Just not going to talk about names.
Sure.
And it was, they were kind of struggling with, well, how do we know it's water resistant? And which was one of the features they wanted to do. So they said, well, watches, like divers' watches. One of the people on the team was a scuba diver and says, well, my watch says it's good to 50 meters. They must have something that does that. So they looked up the Swiss watch industry's set of standards and they pulled one of those out and they said, oh, this isn't too hard. We only want 1 meter. So we get a big bucket of water and the standard says you put it at 1 meter. And it was really just for a few seconds. You expose it to that stress, you pull it out, shake off the excess water, And if it's still working, it passes.
Oh, that was it.
That was it. And if it's a 50-meter one, then they would pressurize the water basically and replicate it, or they would actually go find some place that was 50 meters deep and take it down there and bring it back up and see if it still works.
They told somebody to go jump in a lake, huh?
Yeah. I mean, that was basically the way they standard were. And they had a way to, in a lab, control the amount of water pressure.
Sure.
And it was pretty expensive to do it for the really deep stuff. But these guys they figured people might wear this swimming and your arm stroke might go for a meter. They might see lower ones, but let's start somewhere. So they did a 1 meter test. And then they put all these samples on. It was Friday afternoon. They put the samples on the bench and they came back next week and they said, oh, we've got these samples. And they were all working. So let's do some more testing. And so they put it in a chamber. I think there was a high temperature of some sort. And on Friday, every single one of them had failed. And what they found out was that their devices really weren't all that water resistant. So a bit of water got in, but the water was tap water. It was just water. It wasn't deionized water. It wasn't pure water. It wasn't clean or anything like that. And it wasn't deliberately dirty so that they could detect if it got in there or put tracers or markers in it. And after a week, this little battery-powered device had just enough little voltage gradients going on that little bit of water sitting across these traces and across these components caused corrosion to occur. It just took a week for it to occur. And then when they put it in the chamber at a little bit higher temperature, it sped it up. And then they all failed for corrosion. Now, temperature was a contributor to that.
Yeah.
And so they dismissed it and said, well, we passed the resistance test, so it couldn't be water. There was something else. So they looked at their processes and handling and everything else and figured, we can't find anything. So that was a fluke. And it always boggles my mind, why did fluke instruments name themselves Fluke when they were actually trying to do test equipment looking for flukes?
Maybe that's why.
Maybe that's why. And so I think they shipped something like 75,000 units. Their first sale, it was in the holiday period, and 50,000 failed within a week.
Oh, my.
Yeah. And so they had to reset and refocus on what they're doing. And that's when I learned about this process they use. And I'm like, corrosion does take time. And if you're looking for water resistance and the standard is based on a mechanical system, and if there's water under the glass kind of thing, that's what they call a failure. But they don't put that in the standard. So if it's still working, you don't have a way to tell if there's water in it. You have an opaque system. And that just baffled their mind. What do you mean these standards don't apply? Like, well, they do apply, but you have to be careful what you call failures and how long it takes for them to occur and things like that. You got to understand the failure mechanisms. And storage, I saw a presentation years and years ago by somebody in the auto industry, and they were saying, a large percentage of failure mechanisms that cause vehicles to fail are due to them being stored, being parked. Taxis that get, 200,000 miles in a year, they run and run and run and run. And you change the oil and they just keep on running. But a family car that only gets used for, 40 miles twice a day, spends vast majority of its time parked. And that's really degrading to many parts of the system. And so storage itself is a stressor on so many things.
Yeah, that's a good point, because it depends on the use case of your product.
Right.
Yeah.
It really is. That's in the medical industry actually addresses it so often, especially with drug delivery systems and chemical systems, is the storage life. And they have all kinds of protocols to do that. But I found it is tough to accelerate storage unless you really, really know the failure mechanism.
Yeah, in most cases it was, well, like you said, temperature and humidity
Yep.
were ways to simulate extended storage. Yeah. And in my particular example, it wasn't so much the liquid that parts were exposed to was meant to simulate a viscous solution without really using that solution. So
you're not talking
something...
about artificial sweat, are you?
Yeah, an artificial bodily fluid.
Yeah.
And yeah, there was just something made up in the chemical reaction of the solution degraded the plastics of the part, so that in later mechanical tests they didn't fare so well.
Yeah.
But to really get to the root of that problem, that took quite a bit of engineering detective work to figure out that lab-based solution was what was really causing the problem, that it wasn't necessarily the design, but the test method.
Yep. And there's circumstances like that where if you're doing, say, a thermal cycling test and the lab needs to shut down for maintenance, or it's a long weekend and there's nobody there to monitor it or whatever, and it sits idle for 3 days, for example, there's still thermal cycling going on. And many of us forget that the heating and air conditioning units in the building are going to cycle, and it's going to cause some stress. And if you ignore it, you're going to undershoot your analysis. I remember one of my favorite ones, it wasn't really storage. It was, they would take it off of one set of equipment for testing and put it on a cart and then roll it to another part of the building for where that testing equipment was. And the only reason I heard about this one was that it only happened on swing shift. And it didn't happen during day shift. And so they were really looking at, are they doing the same process? Are they not? And is it going after the operators and all this other stuff? And turned out that during the day, this one hallway was open, that the doors did not have, they had pretty smooth transoms. So this cart, which had hard wheels on it, wouldn't bounce as much or hit these bigger transoms with swing shift had to use to get to this point A to point B. They had a different route.
Oh.
And the only reason I found out about it is I met all the engineers and talked to everybody through the day and saw the process and saw them move it, which wasn't even a factor that was even in discussion at all. And I didn't think anything of it. And then swing shift comes up, and I started my career in industry on swing shift. So I knew they were brilliant, wonderful people. So there's got to be something going on here. So I said, I'm just going to stay a little longer and watch the process again. I need to understand it. And they went over this door jam that just rattled the daylights out of this cart. And knowing a little bit about failure mechanisms, going, I don't think a shock test was part of this transportation system. And it turned out that was the nature of the failures. These things were getting blasted by a huge shock, and they were pretty sensitive test and measurement equipment. And so it really didn't work that way. And I like, that might be the problem. and
it was.
It was, yeah. And so I don't remember what they did. If they took out the transom on the door, or they got soft wheeled tires on their cart, or it was some variation of that. I said, why don't you just give them a key to that door over there that for some reason you close on swing shift? It's like, okay, but whatever. It was, when you're doing a sequence of testing, the handling, the storage, the orientation, sometimes how things are, where, the previous effects accumulate or cause diffusion in a certain direction. It just, you can't put anything to bed without checking it. It's amazing.
And sometimes you can sit at your desk and think about things to check. But like in your last example you just mentioned, you had to be there and be participating with the people and see the product moving to actually catch what the real problem was, because nobody had thought about that.
Yeah. Now, the other side is that you get really brilliant people that use the storage periods to their advantage to get higher yields. We had a temperature sensitive product that would go into this lab that was temperature controlled, and it was because of the mass of the product, it took hours for it to come to temperature for the types of testing they were doing. And it was a temperature sensitive test. It had to be at, say, 20C or whatever it was, and within a small range, and then they could adjust for it off of that. But if it was too far out of that range, or if the bulk of the material wasn't at that room temperature, the test would give you faulty, misleading results. But the folks doing the testing were under pressure to improve yield, which was ridiculous because they're not in charge of creating the product. They're testing it.
So they were in charge, not throughput of the lab, but the actual yield of the product.
Yeah, they were like, "Why are we failing so many of them?" And it was like, "Why are you asking them?" And so they were under this pressure, and so they would, well, we need extra space, so they'd roll the products that failed the first time. They'd roll that out the backside of the lab into the afternoon sun, and then say, well, before the end of the day, we need to retest it. So they'd roll it back in, and it would not have time to come to temperature anymore. But it would be, they was in the lab for an hour or two, but it'd just been sitting out in the sun. And so the bulk of it was still pretty warm, and it would pass. And they knew this. And so they would pass, and then they'd say green sticker, ship it. But it was the function of, why are you putting pressure on the people actually telling you whether your product's good or not, so that they then feel the need to alter the process some.
Yeah, they need to be independent.
Yeah.
Of the results of the test.
So the idea of storage here in that case was a critical part of the testing process in order to get the material to the proper temperature. And by shortcutting that or playing with it, they were able to manipulate the results they were getting. But it was odd that, the original design of the testing was it goes in the evening and then it sits overnight and has plenty of time for this mass to come to temperature. But it didn't account for the social pressure, for the lack of a better word, to take shortcuts or alter this storage part of the process.
I don't know that I would have picked up on that either.
Well, they told me.
What? Right.
They had a lot of trust in me because they had a problem with one cart with just giving them all kinds of fits and was failing all kinds of products. But if they measured it with the other cart, it would pass. And I looked at the two carts and I said, they're supposed to be identical, right? And he says, why does the leads on this one have a little red hinge on it, and this one has a blue hinge on it? And usually test and measurement people don't put fashion as a criteria in their product design.
Yeah.
If you want a red one to match your coat or something and a blue one to match what? And I was like, what? Are these different? So I looked at the catalog, and one was a 4-point resistance probe and the other one was a 2-point resistance mode, which included the contact resistance then. So depending on who was using it, if there was a light touch, they had more resistance. And if they had a real heavy touch, they made good contact and had lower contact resistance, where the 4-point probe automatically eliminated contact resistance. And so they were getting wildly variable results depending on who was using the 2-point probe. And so they were like, you're a genius. And so anytime they were having problems, they'd call me up and I'd come work with them. But some of it was, really? You do that? You don't have enough time for that to cool off. It's like, but they pass.
Well, and again, I know you and I have talked about it before, just the role of reliability engineers being an independent viewpoint of things. And yeah, this is just another example of that. Of you're not part of the daily test lab activities, and you notice, because you're detail-oriented reliability engineer, you notice the color on the probe, and that means something. And just helping to identify what those are and figuring out what's really going on.
Oh, I figure half of our listeners just diagnosed me with OCD, but
for noticing a color on a probe. but it goes to show you have to show up at the place where it's happening and talk to the people and look at what they're doing.
Yeah.
And just be there and be present.
Well, there's also, don't assume that if you put it on the shelf, it's going to be okay. Back to your original story. It's, or put it on a cart and roll it. It's think through every step of the way and every handling, turn, twists, what does one test carry over to another test? And, if that's accelerant, does that interact with we can assume all day long that they're independent. But unless you check it, you don't know.
Yeah.
And
it can have huge consequences on your test results and the decisions that you make with it.
That's right. That's exactly right. Although, as much as we both enjoy doing a good failure analysis, let's get the design right in the test right. That's right. All the sequencing right. And then we get the results that are useful and meaningful. And I don't know. I do like breaking things though. So
on purpose.
Oh, of course.
And that is more rewarding. Yeah. I agree.
Yeah. No, cool. So it's interesting discussion. It brought back some old memories of some of this stuff. But it goes to the point is you got to think this stuff through. So if you're listening to this and have a question, or if you're looking at setting up testing, or you're getting odd results or something like that, or have some advice, let us know. Head over to accendoreliability.com/go/SOR. Dianna and I and the other hosts of the show are available through LinkedIn and on our about pages on the site. And yeah, we certainly enjoy hearing from you and topics and questions. As I mentioned in the last episode, is that it's fueling more and more, a higher and higher percentage of our topics. And so we really do appreciate it. And hopefully it's useful for you. You get an answer or get some ideas or insights. But we do like having you as part of the show. And so thanks, Dianna, for bringing this one up. Hopefully it'll spark a handful of discussions, because I know many of our listeners are dealing with not enough samples, and how do you do appropriate testing along the way. And we just added more complication to it, I think.
Yeah. Well, I mean, it's just some gotchas to watch out for. That's all.
Yeah.
And I'm sure everybody has a story with that. And it's helpful to hear other people's experiences, because there's things that you didn't think to look for. Now you know.
Yeah, perfect. Well said.
So thanks for sharing your stories, Fred.
No problem. Thanks, Dianna. We'll talk to you again soon.
Okay. Bye, Fred.
Bye-bye. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.